12,900 years ago, something snapped in the North Atlantic. Within a single human lifetime, northern Europe dropped by an estimated 10 to 15 degrees Celsius. The Sahara dried, tropical rain belts shifted, ice returned to places that had been thawing for 2,000 years. We have a name for that event now, the Younger Dryas. The cause, according to ice cores and ocean sediment, was the collapse of the Atlantic conveyor belt. And right now, every major instrument we have pointed at the same conveyor belt is screaming the same word at us: slowing. So if it happened once, in a window as short as a decade, what exactly are we looking at when the data shows it happening again? If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as this story unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about what's happening to the Atlantic. Now, let's get into it. Part 1. The conveyor belt that built Europe. I want you to picture something for a second. Picture the entire Atlantic Ocean as a single, continent-spanning machine. Not a body of water, a machine. A heat redistribution engine the size of a hemisphere, pumping warm water north and cold water south on a loop that takes roughly 1,000 years to complete one full revolution. That machine has a name. Scientists call it the Atlantic Meridional Overturning Circulation, which is a mouthful, so most of us just call it the AMOC. And here is the thing nobody tells you about the AMOC. Without it, Europe is not Europe. London is at the latitude of Hudson Bay. Think about that for a second. Hudson Bay, where polar bears live, where the ground stays frozen for 8 months a year, where the average January temperature is somewhere around -20 Celsius. London should look like that. Berlin should look like that. Paris should look like that. The reason none of those cities are buried under permafrost right now, the reason Norway can grow wheat at the latitude of southern Greenland, the reason Western Europe is roughly 5 to 10 degrees Celsius, warmer than every other landmass at its same latitude on this planet, is because of one thing. That ocean engine, the AMOC. And according to a converging stack of peer-reviewed studies published in the last 5 years, that engine is failing. I want to say that again, because it is the kind of sentence that slides past you on the first listen. The engine that built modern Europe, the engine that allowed continuous human civilization in the North Atlantic basin for the last 12,000 years, the engine that is the single largest mover of heat in the climate system is failing. Not in some distant future. Now, measurably, and faster than every climate model on Earth has been telling us. So how does this thing actually work and why is it dying? Let me walk you through it, because once you see the mechanism, you cannot unsee it. The AMOC starts down in the equatorial Atlantic, where the tropical sun is hammering the surface of the ocean and turning it into the hottest, saltiest water in the basin. Hot because the sun is relentless on the equator. Salty because in the tropics, evaporation outpaces rainfall, so water leaves as vapour and the salt stays behind. That hot, salty water gets picked up by the trade winds and pushed north. It moves up the eastern seaboard of North America as part of the Gulf Stream, that famous warm current you have probably heard about your whole life. The Gulf Stream is essentially the southern leg of the AMOC. It carries an absolutely staggering amount of heat, roughly 1.25 petawatts of energy at peak transport. To put that number in something you can actually feel, that is about 100 times the total electricity generation of every power plant on the planet, combined. All of it. Every coal plant, every nuclear plant, every solar farm, every wind turbine, all of it added together times 100, just being silently shoved north along the coast of North America by the Atlantic Ocean every single second of every single day. That heat does not stay in the water. As the warm Gulf Stream water flows northeast toward Europe, it releases that heat into the air above it. The prevailing westerly winds, the ones that have shaped European weather for as long as there has been a Europe, then carry that heat onto the continent. That is what builds European winters. That is what melts off the snow in February instead of June. That is what made the agricultural civilizations of Northern Europe possible in the first place. You cannot run a continent on the latitude of Hudson Bay without a continuous permanent transfer of equatorial heat into your atmosphere. And the AMOC is the only thing on Earth doing that transfer at that scale. Now here is the part that is hard to picture, but absolutely critical, because it is where the engine is breaking. By the time the warm water reaches the seas around Greenland, Iceland and Norway, and the Labrador Sea between Canada and Greenland, it has cooled dramatically. It has given up most of its tropical heat to the European atmosphere, and here is the trick, the part that makes the entire global ocean conveyor work. That cold water, having lost its heat but kept its tropical saltiness, has now become the densest seawater on the planet. Cold, dense water, salty, dense water, cold and salty, dense water, and cold, salty, dense water sinks, hard. It sinks in enormous columns several kilometers tall. Oceanographers call this North Atlantic deep water formation, and it is the pump. It is the literal mechanical engine of the entire global ocean overturning. Without that sinking, the conveyor stops. The water that should be coming south at depth doesn't come south. The water that should be moving north on the surface doesn't get pulled north. The whole loop breaks. Once that cold, salty water has plunged down to 2, 3, sometimes 4 kilometers below the surface, it begins flowing southward, slowly, through the abyssal Atlantic. It crosses the equator at depth. It keeps going. It reaches Antarctica, where it merges with the Great Antarctic Circumpolar Current. From there, the cold sinking water spreads out into the global abyss, eventually rising back to the surface in the Indian Ocean and the Pacific, and beginning the long, slow journey back to the Atlantic to start all over again. The full circuit, top to bottom, surface to abyss, takes about 1,000 years. 1,000 years for a single drop of water to complete the loop. That is the timescale of the global ocean conveyor. That is how slow and how enormous this system is. And it has been running, more or less continuously, for the entire span of human civilization. Every empire, every farm, every city in the Atlantic basin has been built on top of this machine. Quietly, reliably, like the heating system of a building you've never bothered to look at because you have always been warm, but the heating system is breaking. In 2018, a team led by Levka Caesar at the Potsdam Institute for Climate Impact Research published a paper in Nature, the highest impact journal in the world for this kind of research, and they did something clever. Direct measurements of the AMOC have only existed since 2004, which is way too short a record to know whether you're looking at a trend or just normal ocean weather. So Caesar and her team used a fingerprint. They reasoned correctly that if the AMOC is slowing, then the warm water it normally carries north won't be reaching the subpolar Atlantic, which means that one specific patch of ocean, south and east of Greenland, should be cooling, or at least not warming, while the rest of the planet warms. They went looking for that fingerprint in over 100 years of sea surface temperature records, and they found it. A cold blob sitting right where the physics predicted, surrounded by anomalously warm water along the Gulf Stream. They used that fingerprint to reconstruct AMOC strength all the way back to the 1870s, and the answer they got was sobering. The AMOC has weakened by roughly 15% since the middle of the 20th century, and it is now in its weakest state in at least 1,000 years. A separate paper that same year, by David Thornalley and his team at University College London and Woods Hole, used something even more powerful. Sediment cores, mud, basically, extracted from the bottom of the Labrador Sea and the abyssal Atlantic, layer by layer, going back through the entire Common Era. 1,600 years of climate history, written in the size and shape of grains of silt and the species of microscopic foraminifera fossils. The conclusion of that paper was even more disturbing than Caesar's. The current weakness of the AMOC, according to Thornalley's mud, is unprecedented in approximately 1,600 years. 1,600 years? Roman emperors were still being crowned the last time the Atlantic conveyor moved this slowly. The fall of the Western Roman Empire was happening in real time, and we are now, according to the sediment record, in a weaker state than the AMOC has been in at any point since. That is the system we are talking about. That is the engine that has been quietly running underneath every European harvest, every American hurricane season, every African monsoon, for as long as anyone alive can remember. And we have the receipts now, in 5 different research teams, in 3 different methodologies, in over a century of data, that it is failing. So the next question, the obvious question, the one that every viewer has to be asking by this point, is the simplest and most terrifying one of all. If the AMOC is the thing that built Europe, and the AMOC is now in the weakest state it has been in since before the fall of Rome, what exactly happens next? Because the answer is hidden in a patch of ocean that is doing something no other patch of ocean on this planet is doing. It is getting colder. Part 2, the cold blob, the only place on Earth, getting colder. There is a satellite map I want you to imagine. It is a global temperature anomaly map, the kind you have probably seen 100 times by now. Red, where the ocean is warming, blue where it is cooling, neutral where it isn't doing much. And if you pull up that map for the satellite era from the late 1970s to today, what you see is very simple. The whole planet is red. The Pacific is red. The Indian Ocean is red. The South Atlantic is red. The Mediterranean is red. The tropical oceans are red. Even the Arctic, especially the Arctic, is the deepest blood red on the entire map. Every ocean basin on Earth is warming, and the warming is happening at a rate that is unmistakable on the satellite record. Every ocean basin except one. There is one place, one single patch of ocean on the entire planet that is bucking the trend, sitting just south of Greenland, just south of Iceland, in the subpolar North Atlantic, a roughly oval region of water about the size of Western Europe. And on the temperature anomaly map, that patch is blue. While everything else is red, that one piece of ocean is colder than it used to be. Some of it is much colder. The cold blob has been documented continuously in the satellite record since the late 1970s, and the cooling has not gone away. If anything, it has deepened. Scientists have, over the last 2 decades, gone through every plausible explanation for why this specific patch of the ocean would buck the global trend. They've looked at cloud cover, they've looked at wind patterns, they've looked at ocean mixing, and one by one, every alternative explanation has fallen short. There is one explanation, and only one, that fits the geographic specificity of the cooling, the magnitude of the cooling, the timing of the cooling, and the physics of how heat moves through the North Atlantic. The AMOC is slowing down. Less warm water is reaching the subpolar Atlantic, and the surface of the ocean in that region is therefore not warming the way it should be. And here is the part that should give you a small, cold feeling in the back of your skull. The fingerprint of a slowing AMOC is not just a cold blob south of Greenland. The fingerprint is a cold blob south of Greenland surrounded by anomalously warm water along the Gulf Stream pathway. Because if the AMOC slows, the warm water that should be moving past the Gulf Stream and continuing north toward Europe gets bottled up. It piles up in the Western Atlantic, off the coast of the United States, and warms anomalously fast, so you get a very specific signature. Cold patch over there, hot patch over here. A kind of climate Rorschach test where, if you squint, you can see the ghost of an ocean current that is no longer doing its job. That is the exact pattern that Caesar's team identified in 2018. That is the fingerprint that has been visible in the satellite record for 50 years, and as the years have gone by, the pattern has not faded, it has sharpened. I want to slow down here because this is the part of the story where the science genuinely starts to feel like it is leaning over your shoulder and whispering. We are not looking at a model projection, we are not looking at a simulation. We are looking at actual photographs of the surface of the ocean taken from space every day for half a century. And what those photographs show, with no model assumptions whatsoever, is a regional pattern of temperature change that no other physical mechanism in the known climate system can produce. The cold blob is real. It has been there continuously. And it is the spatial fingerprint of a weakening Atlantic conveyor belt. There is something almost fairy tale about it. The ocean is showing us a clue, in a place where no clue should exist, in a shape that lines up with exactly one cause, like a footprint in the snow that only one creature could have made, and the cold blob is not the only fingerprint. Once researchers knew what to look for, they started seeing the evidence everywhere. The Gulf Stream itself has been observed warming and shifting northward over the last several decades, which is exactly what you would expect if the warm water is no longer being efficiently pulled past it toward Europe. The boundary between the cold Labrador Current and the warm Gulf Stream has been shifting, with subtropical foraminifera, those tiny shelled plankton, showing up in Labrador sea sediments where they shouldn't. The Atlantic Intertropical Convergence Zone, the band of equatorial rain that determines whether the Sahel gets a monsoon, has been creeping southward, exactly as predicted if cross-equatorial ocean heat transport has been weakening. And here is the one that should hit close to home for a lot of you watching. Sea level rise along the United States East Coast, New York, Boston, Norfolk, Charleston. Tide gauge data over the last several decades shows sea levels rising at 3 to 4 times the global mean rate in those cities. 3 to 4 times the global mean. That is not a small anomaly, that is enormous, and the standard climate science explanation is a 3-component model. Some of the rise is thermal expansion, the simple fact that warmer water takes up more volume, and that component is roughly uniform across the globe. Some of it is land subsidence, where the actual ground is sinking due to local geology and groundwater extraction, and that component is region-specific but well documented. And the third component, the one that explains the rest of the gap between the East Coast rate and the global mean, is ocean dynamic effects driven by AMOC weakening. When the AMOC slows, water piles up along the Western Atlantic. That piled up water has to go somewhere, and where it goes is up, onto the coast, into the streets, through the basements, past the seawalls. If you live in any of those cities, if you have watched the king tides creep higher every year, if you have seen Norfolk's flood maps redraw themselves every 5 years, if you have noticed Miami beginning to flood on sunny days with no storm in the forecast, you have been watching the AMOC weakening expressed in real, measurable, soggy shoes on the pavement reality. It is not a future threat. It is a present-day fingerprint, recorded in every tide gauge from Maine to Florida. And there is more. The cold winters of 2009 and 2010 in Northern Europe, the brutal cold snap of 2017 and 2018, the persistently cool grey summers in the British Isles in the early 2020s, all of these have been studied and connected by various papers to the strength of the cold blob and the meandering jet stream behaviour associated with a weaker AMOC. Now, no individual weather event is climate attributable in a strict sense. You cannot say this specific blizzard happened because the AMOC is slowing. But the collective pattern, the way Northern Europe has begun to behave in a manner that diverges from a simple, uniformly warming planet, is consistent with the regional signature that the physics predicts. People in the United Kingdom right now are living on average in a slightly different climate than their grandparents did, in a way that is not just warmer, but stranger, less predictable, with odd cold spikes that the rest of the warming world isn't experiencing. So pull back for a second and look at what the data is actually doing. We have a cold patch where there should be no cold patch. We have a shifted Gulf Stream. We have shifted plankton. We have a shifted equatorial rain belt. We have anomalously fast sea level rise along the entire United States east coast. We have unusual cold snaps in Northern Europe. And every single one of those signals is consistent with the same single cause, a weakening AMOC. It is the kind of pattern that, if you saw it in a detective novel, would feel almost too neat. The ocean is leaving fingerprints everywhere, in space, in paleoclimate sediment, in coastal floods, in agricultural patterns, in the pixels of weather satellites. And the question, the only real question, is no longer whether the AMOC is weakening. The science settled that several years ago. The question is how fast it is weakening, and how close it might be to the kind of nonlinear behaviour the paleoclimate record tells us this system is fully capable of. Because if the cold blob is the fingerprint of a slowdown, then the ocean has been signalling its own decline for half a century in plain sight, on every weather map you've ever seen. And we have only just begun to read what it has been writing. So if the surface of the ocean is telling us this, the obvious next question is, what does the abyss below it look like? What about the part of the conveyor belt that you can't photograph from space? Because that is where the real engine actually lives, and there is exactly one set of instruments on this planet that has been measuring it directly, in real time, for the last 20 plus years. Part 3, rapid at 26.5 degrees north, the first direct measurement. 26.5 degrees north. Memorize that number. Because that line of latitude, an invisible mathematical line stretching across the Atlantic Ocean from Florida to the western coast of North Africa, is where a small group of British, American, and international scientists decided 2 decades ago to do something nobody had ever done before. They decided to wrap a single line of latitude in instruments and measure, continuously, in real time, the actual mechanical strength of the Atlantic conveyor belt. Not from satellites, not from sediment, not from temperature fingerprints, directly, the flow of water, in motion, in sverdrups. You may not have heard the word sverdrup before, but it is the unit oceanographers use to describe really big ocean flows. 1 sverdrup is 1 million cubic meters of water per second. So when scientists tell you the AMOC moves about 17 Sverdrups, what they mean is that 17 million cubic meters of water are moving north past that line every single second. To put that in something you can picture, the entire flow of the Mississippi River in a single second of AMOC transport is being pumped north past that line about 1,000 times over. The AMOC moves more water in a single second than every river on Earth combined moves in nearly a minute. That is the scale of the engine we're talking about, and in 2004 scientists started measuring it. The array is called Rapid-MOCA-W BTS, which is one of those instrument names that tells you immediately 3 different agencies were involved in funding it. RAPID is the United Kingdom's National Oceanography Centre programme. MOCA is the US National Science Foundation's programme at the University of Miami. WBTS is the National Oceanic and Atmospheric Administration's Western Boundary Time series. Together, these 3 programs operate a network of moored instruments stretching across the Atlantic at 26.5 degrees north, plus a set of bottom pressure sensors on the seafloor, plus a clever trick involving the transatlantic submarine telephone cable across the Florida Strait, which can be used to measure the integrated flow of the Gulf Stream by detecting the tiny electromagnetic signal generated when salty conducting seawater moves through the Earth's magnetic field. Add it all together and you get a continuous real-time measurement of how much water is overturning across that latitude, 24 hours a day, 365 days a year, going on 20 plus years, and here is what RAPID has measured. The long-term mean transport across 26.5 degrees north is approximately 17 Sverdrups. There is significant year-to-year variability. There are seasonal fluctuations. The ocean is a noisy place, and a single year of RAPID data taken in isolation might tell you anything from 12 to 22 Sverdrups, depending on the year. But over the 20 plus years of continuous record, a pattern has emerged. Specifically, between 2004 and 2012, the array observed a substantial weakening. Approximately 3 Sverdrups, or roughly 15% of the total transport, gone. That is statistically significant, even against the background noise of normal ocean variability. David Smead and his team published the analysis in 2018 in Geophysical Research Letters, and the conclusion was sobering. The post-2008 mean of the AMOC, as measured directly by RAPID, is meaningfully weaker than the pre-2008 mean. The trend has not steepened further in the years since, but it has not reversed either. The AMOC, as far as the direct measurement record can tell us, is sitting at a plateau roughly 15% below where it sat when we first started watching it. There is a healthy scientific debate, which I want to acknowledge, about how much you can read into 20 plus years of RAPID data. The AMOC has natural variability on timescales from years to decades to centuries. A 20-year record is, in some real sense, too short to definitively establish a long-term trend. The honest position from oceanographers like Susan Lozier at Georgia Tech is that the RAPID record alone is consistent with both a long-term anthropogenic weakening and a phase of normal multi-decadal variability that will eventually reverse on its own. The data alone cannot distinguish those 2 possibilities, but, and this is the point of the converging evidence framing that is going to come back again and again in this video, the RAPID record does not stand alone. The fingerprint analysis from CESA 2018 does not stand alone. The paleoclimate sediment record from Thornalley 2018 does not stand alone. Each of these methods has its own limitations. Each of them, in isolation, is debatable, but they are converging. They are all pointing in the same direction, and they are all pointing in the direction the basic physics of freshwater dilution and density-driven sinking would predict, given the rate at which Greenland is currently melting. There is also a second array I have to mention briefly, called OSNAP, which stands for Overturning in the Subpolar North Atlantic Program. It started in 2014, and it is positioned much further north than RAPID, in the actual region where the cold sinking takes place. OSNAP gives you a closer look at the core of the engine, and the OSNAP record so far, while shorter, has been consistent with the broader picture of weakening overturning, particularly in the eastern subpolar gyre. The combination of RAPID at 26.5 degrees north, OSNAP in the subpolar region, the transatlantic Argo float network, and the satellite altimetry record is the most comprehensive set of ocean monitoring instruments ever pointed at a single circulation feature in human history, and every one of them is telling the same story. The AMOC, the engine, is running slower than it used to. Not catastrophically slower, not yet, but measurably slower, persistently slower, and there is no observational signal anywhere in the data suggesting that the slowing is reversing. The rapid array is the gold standard direct measurement of the AMOC, and it is one of the great unsung scientific instruments of the 21st century. It does not make headlines, it does not have a dramatic name. It is just a string of yellow buoys and concrete-anchored moorings sitting quietly across the Atlantic, and a quietly humming submarine cable in the Florida Strait, and a small army of scientists who pull the data every few months and crunch the numbers and publish papers in journals most people will never read. And what they have been telling us, patiently, year after year, is that the largest heat engine on planet Earth is, in fact, slowing down. Now here is where the story gets really interesting, because the next question is the obvious one. Why? What is actually causing the engine to slow down? And the answer is happening right now on a frozen island just to the north of the cold blob, where ice that has been stable for over 100,000 years is now sliding into the sea at a rate that is unlike anything ever measured by science. So let's go to Greenland. Part 4, Caesar, 2018 and the 1600-year low. Before we get to Greenland, I want to spend a few minutes with a paper that, more than any other in the last decade, dragged the AMOC story from a niche, oceanographic concern into mainstream climate science. Because the science world doesn't usually move quickly. Decades-long debates over methodology and interpretation are normal. But once in a while, a paper drops that everybody, friend and skeptic, has to take seriously. And in 2018, 2 of those papers dropped within months of each other. Both in Nature, both pointing at the same conclusion. The first was Levka Caesar's 2018 study. The second was David Thornalley's. Together they did something that the science community had been trying and failing to do for 30 years. They reconstructed the recent history of the Atlantic conveyor belt using 2 completely independent methodologies, and they got the same answer. Caesar's team approached the problem the way detectives approach a missing person case. They couldn't measure the AMOC directly back into the past, because the direct measurement record only goes back to 2004, but they could measure the consequences of past AMOC behaviour. They could look at what an AMOC of a given strength does to the surface of the ocean. So they ran climate models with a wide range of AMOC strengths, looked at the resulting sea surface temperature patterns, and identified a specific spatial fingerprint that varies in lockstep with overturning strength. That fingerprint is the cold blob plus the warm Gulf Stream pattern we walked through in Part 2. Once they had the fingerprint, they could go back to the actual observational sea surface temperature record, which exists in usable form back to the 1870s, and translate that record into a continuous estimate of AMOC strength over more than 150 years. The result was published in Nature in 2018, and the conclusion was clear. The AMOC has weakened by about 15% since the middle of the 20th century. The bulk of that weakening, statistically, has occurred since around 1985, which lines up neatly with the period of accelerating warming and accelerating Greenland ice loss. And the absolute strength of the AMOC, as inferred from the fingerprint, is now weaker than it has been at any point in the observational sea surface temperature record. Not by a little, by a lot. 2021, Caesar and Stefan Rahmstorff and Nicholas Boers, all giants in this field, published a follow-up in Nature Climate Change. They extended the analysis with additional proxies and additional data. They ran consistency checks against multiple climate model ensembles. They confirmed the original 2018 result and, if anything, strengthened it. The AMOC is not just weak, it is weaker than it has been in centuries. But the fingerprint method has a limitation. It can only go back as far as the sea surface temperature record allows, which is to say, the late 1800s. To go further back, you need physical proxies preserved in the geological record, and that is where Thornalley's team came in. Thornalley and his colleagues at University College London and Woods Hole Oceanographic Institution went after the problem from a completely different angle. They went and pulled up cores of mud from the bottom of the Atlantic. I want to spend a moment on the science of paleoceanography, because it is one of those fields that, once you understand what it does, feels almost magical. The abyssal ocean floor is a graveyard. Every year, a slow, continuous rain of dead microscopic organisms plus tiny grains of mineral sediment carried in by ocean currents settles on the seafloor and accumulates, layer by layer, year by year, century by century. In some places, that sediment accumulation is so undisturbed that the layers preserve a continuous, readable record going back tens or hundreds of thousands of years. You can pull up a sediment core from the right spot, slice it like a layer cake, and read history 1 millimeter at a time, 20 centuries on a single piece of mud the length of your arm. Thornalley's team focused on 2 specific sites in the abyssal Atlantic, and they used 2 complementary proxies. The first was sortable silt grain size in cores from the Iceland Basin. Sortable silt is exactly what it sounds like, the fraction of mud particles that fall into a specific size range that is sensitive to current speed. Faster bottom currents carry larger grains. Slower bottom currents drop larger grains and only carry the fine ones. By measuring how the grain size distribution of sortable silt changed through time, you can reconstruct century by century how fast the bottom currents at that location were flowing. And the bottom currents at that location are driven by the AMOC. Faster grains, stronger AMOC, finer grains, weaker AMOC. The second proxy was foraminifera. These are tiny shelled plankton, microscopic single-celled organisms that build delicate calcium carbonate shells and live in specific parts of the ocean, depending on water temperature, salinity, and depth. When they die, their shells fall to the seafloor and get preserved in sediment indefinitely. By cataloguing which species of foraminifera show up in which layers of a Labrador Sea sediment core, you can reconstruct the location of the boundary between the cold Labrador Current and the warm Gulf Stream water at any given moment in the past. That boundary moves north and south depending on the strength of the AMOC. So you have 2 completely independent paleoceanographic proxies, one based on the speed of bottom currents, one based on the location of a thermal front, and they should agree if they are both faithfully recording AMOC strength. They agreed. Both proxies, independently, told the same story. The AMOC was relatively stable for most of the last 1600 years, with normal variability of a few % up or down, the kind of natural ocean breathing you would expect over a millennium. Then, beginning around the year 1850, both proxies showed a substantial persistent weakening. The conveyor was slowing down. By the modern era, both proxies were showing AMOC strength at or near a 1600-year low, exactly the same conclusion the fingerprint method had reached, by a totally different route. The convergence was not a coincidence, it was a corroboration. There is something useful to note about the timing of that 1850 inflection point. 1850 is roughly the end of the Little Ice Age, the cool climate period that lasted from about 1300 to 1850 across the Northern Hemisphere. The end of the Little Ice Age would have produced a freshwater pulse from melting sea ice and shrinking ice caps in the high-latitude North Atlantic, exactly the kind of input that would weaken AMOC. So the historical context fits, the timing fits, the mechanism fits, and the modern continuation of that weakening is consistent with the modern continuation of melting in the same region, except now driven by anthropogenic warming rather than natural recovery from a cool period. Take a step back and look at what those twin 2018 papers actually accomplished. They took a system that, prior to the mid-2000s, had basically no continuous direct measurement, and they reconstructed its behaviour over more than 1,000 years using 2 completely independent methodologies, and the methodologies agreed. The AMOC, the Great Atlantic Engine, is in its weakest state in approximately 1,600 years. That is not a model projection. That is not a future scenario. That is the empirical, observational, peer-reviewed, multiply-replicated answer to the question, where are we right now? And here is where the story gets uncomfortable, because Caesar 2018 and Thornalley 2018 were the papers that crystallized the concern, but they were not the only ones. They were the leading edge. The follow-up Caesar 2021 paper came next, then Bohr's 2024 in Nature Geoscience using salinity proxies, then Portman 2026 in Science Advances, which we'll get to in a few minutes, suggesting that climate models have been systematically underestimating how fast the AMOC actually responds to warming. And running underneath all of it, the Ditlevson 2023 paper in Nature Communications, applying tipping point mathematics to the question of when the AMOC could fully collapse. 5 major papers, 5 different groups, 5 different methodologies, all converging on the same direction of change, all published in the highest impact venues in the field, and all of them building on the foundation that Caesar and Thornalley laid down in 2018. So the question is no longer whether, it is no longer if. The question, as the science has matured, has shifted to how fast and how far. And how fast it turns out depends almost entirely on how much fresh water continues to dump into the North Atlantic over the next several decades. Which brings us to the place where most of that fresh water is coming from, a frozen island roughly the size of Mexico, sitting just north of the cold blob, that is currently bleeding into the ocean at a rate that has accelerated continuously since the early 2000s, and that, according to satellite gravity measurements, may be on the verge of crossing irreversibility thresholds of its own. Part 5, Greenland is bleeding into the North Atlantic. Greenland is one of those places that is hard to picture if you have never seen it. 2.5 times the size of Texas. 80% of it covered in an ice sheet up to 3 kilometers thick, the second largest body of ice on Earth after Antarctica, holding enough frozen water to raise global sea level by about 7.5 meters if it all melted. That ice sheet has existed, in roughly its current configuration, for over 100,000 years. It survived the end of the last glacial period. It survived the Holocene climate optimum about 8,000 years ago when global temperatures were arguably higher than they are today. It has been one of the most stable, predictable features of the Northern Hemisphere climate system for the entire span of human civilization, and right now it is melting faster than at any time in the satellite record. The exact number, according to Grace and Grace follow-on satellite gravimetry data through 2024, is approximately 270 to 280 gigatons per year. A gigaton is 1 billion metric tons. 270 gigatons per year of fresh water pouring off the surface of Greenland and into the surrounding ocean. Cumulatively, since 2002 when Grace first started flying, Greenland has lost approximately 5,300 gigatons of ice. That is enough fresh water to raise global mean sea level by about 1.5 centimeters from Greenland alone in a little over 2 decades, and the rate has been accelerating. The early 2000s losses were lower, the mid-2010s losses were higher. The 2023 balance year was the third lowest year of net surface mass change in the entire 40-year record. And although 2024 was a slightly less extreme melt year than the absolute worst on record, the trend has not reversed. Here is the connection to the AMOC, and this is the part where everything we have been talking about so far snaps together into a single chain of physics. The AMOC depends on the cold North Atlantic water sinking efficiently in the seas around Greenland, Iceland, and the Labrador. That sinking depends on the water being cold and dense. And density, in seawater, depends on 2 things: temperature and salinity. Cold water is denser than warm water, salty water is denser than fresh water. Both effects matter. And in the modern North Atlantic, both effects are being attacked at the same time. The water is warming, which makes it less dense, and the water is being diluted with fresh water, which makes it less dense. And the sources of that fresh water are exactly the things you would expect. Greenland ice sheet melt, 270 gigatons per year. Arctic sea ice melt, with the September minimum extent now down by roughly 40% since the late 70s. Increased high-latitude precipitation, driven by a warmer atmosphere holding more water vapor. An accelerating Arctic river discharge, with the great rivers of Siberia and northern Canada now dumping more fresh water into the Arctic Ocean, which then flows out through the Fram Strait between Greenland and Svalbard into the same patch of ocean where the AMOC is supposed to sink. Add it all up, and you have a freshwater forcing on the North Atlantic that is unprecedented in the satellite record. The water that needs to sink, in order for the AMOC to keep running, is becoming less and less able to sink, because every year a slightly larger volume of freshwater is being poured on top of it, and freshwater floats on saltwater and forms a stable, less dense lid that resists mixing. The mechanism is not subtle, it is not theoretical, it is not contested. It is the same mechanism that drove every previous abrupt climate transition in the paleoclimate record, including the Younger Dryas. We will get to the Younger Dryas in detail in a few minutes, because it is probably the single most important historical analogue for understanding what is currently happening, but for now I just want you to hold this one thought. Greenland is the proximate driver. The ice that has been stable for 100,000 years is now bleeding into the very patch of ocean that, according to every piece of evidence we have, is approaching a tipping point. And the AMOC weakening trajectory we're seeing in the satellite sediment and direct mooring data is exactly the trajectory you would expect, given the Greenland melt rate that satellite gravimetry is measuring. The consequences for the global ocean are not abstract. Already we have observed freshening of the upper layers of the North Atlantic. Already we have observed slowdowns in the formation of Labrador seawater and Denmark Strait overflow water, the two main components of North Atlantic deep water. Already we have observed changes in the subpolar gyre circulation. Every single one of these observations is consistent with the predicted impact of freshwater forcing from Greenland melt on the AMOC. Every single one is happening right now in real time on the scale of decades. And there is a feedback loop hidden inside this story that is genuinely terrifying. As the AMOC weakens, the warm water that should be carried north toward Greenland slows down. That sounds, on the surface, like it should be good for Greenland, because warm water destabilizes glacier termini and drives ice loss. But the geometry is complicated. The warm water that is bottled up in the Western Atlantic doesn't just sit there. It feeds increased ocean heat content along the United States east coast. It also intrudes into Greenland's western fjords through subsurface pathways that don't depend on AMOC strength, and the surface warming in the rest of the high northern hemisphere, which is being amplified by a process called Arctic amplification that has caused the Arctic to warm at roughly 4 times the global mean rate, continues to drive surface melt across the Greenland ice sheet regardless of what the AMOC is doing, so the feedback is asymmetric. AMOC weakening doesn't necessarily slow Greenland melt, but Greenland melt does directly weaken the AMOC, which means the system has a built-in one-way amplification. Greenland feeds AMOC weakening. AMOC weakening doesn't fully shut off Greenland's heat sources, and the loop keeps running faster and faster until the freshwater pulse pushes the system across some threshold. What is that threshold? We don't know exactly. The honest scientific answer is that we have not directly observed the AMOC crossing a tipping point, so we do not have a calibrated value for the freshwater forcing required to flip it. We only know, from the paleoclimate record, that it has happened before, multiple times. 20 plus times during the last 100,000 years, in fact, during what climate scientists call the Heinrich events and the Dansgaard-Oeschger oscillations. Each of those was driven by some combination of glacial freshwater outbursts and atmospheric forcing. Each of them produced abrupt decadal-scale climate transitions across the northern hemisphere of magnitude 5 to 15 degrees Celsius. And all of them happened on a planet whose total ice volume was much larger than ours, which means a smaller fractional melt of a much larger ice sheet was sufficient to flip the system. We do not have a 100,000-year ice sheet to draw on for our freshwater. We have Greenland. Greenland is bleeding 270 gigatons per year, and the rate is accelerating. If you do the math, and you assume the rate keeps climbing on its current trajectory, by mid-century Greenland could be losing 500 gigatons per year or more. Cumulatively, by the year 2050, it could have lost something on the order of 15 to 20,000 gigatons of ice. That is a freshwater volume that begins to look meaningful even on the scale of past Heinrich events, and it is being delivered, not over millennia, but over decades. The chain of physics, again, end to end. Anthropogenic greenhouse gas warming raises global temperatures. The Arctic warms 4 times faster than the global mean. Greenland's surface starts melting more aggressively. 270 gigatons per year of fresh water pours into the North Atlantic. The North Atlantic surface freshens. The freshwater lid resists sinking. North Atlantic deepwater formation slows. The AMOC weakens. The fingerprint shows up in sea surface temperatures, sediment cores, rapid measurements, sea level on the US East Coast, jet stream behavior over Europe, equatorial rainfall patterns over the Sahel. All of those signals are visible right now, and the engine of all of it, the proximate driver, is just to the north of where we are looking, bleeding into the ocean. So the question becomes, how much further can this go before we cross a threshold? And in 2023, 2 scientists in Copenhagen took on that exact question with a piece of mathematics that has been used to predict tipping points in everything from ecosystem collapse to financial crashes. They applied it to the AMOC, and the number that came out of their model was a year, a specific single-digit confidence interval year, and it landed inside most viewers' lifetimes. Part 6. Ditlevsen. 2057 and the mathematics of a tipping point. In July of 2023, a paper landed in Nature Communications that shook the climate science community in a way few papers do. The authors were Peter Ditlevsen and his sister Suzanne Ditlevsen, working at the University of Copenhagen. Peter is a glaciologist and climate physicist, Suzanne is a statistician, and together they applied a piece of statistical machinery called early warning signal analysis to the long-term sea surface temperature record of the subpolar North Atlantic, the very same cold blob region we have been talking about, and they used it to estimate when the AMOC could fully collapse. The number they got was 2057, and the 95% confidence interval ran from 2025 at the lower bound to 2095 at the upper bound. I want to slow down and explain what early warning signal analysis actually is, because it is the kind of thing that, if you describe it as just statistics, sounds dry. But if you describe what it is actually doing, it is genuinely strange and powerful. Imagine a marble sitting in a bowl. The shape of the bowl represents the stable state of the system, and gravity pulls the marble back to the bottom of the bowl whenever it gets pushed off-center. If you give the marble a small nudge, it rolls up the side a little, then rolls back down. The speed of that bounce back depends on the steepness of the bowl. A steep bowl gives you fast recovery, a shallow bowl gives you slow recovery. Now imagine that somehow the bowl is gradually flattening out, the sides are getting less steep. As the bowl flattens, the marble's bounce back gets slower. Its motion gets more correlated, because each push leaves it lingering near where it was nudged, instead of snapping back immediately. The variance of its position grows because it gets pushed further by the same nudge. And eventually, when the bowl is flat enough, a single moderate push can send the marble out of the bowl entirely. That is a tipping point. The mathematics of complex dynamical systems shows that before a system reaches a tipping point, you can detect the bowl flattening by looking at the statistics of the system's motion. Specifically, two things grow as a system approaches tipping: autocorrelation, which is a measure of how strongly each value depends on the previous one, and variance, which is a measure of how widely the system swings around its average. If you can measure those two quantities in a real-world system, and you can show that they are systematically growing over time, you're seeing the statistical fingerprint of an approaching tipping point. This is called critical slowing down. It has been observed and validated in a wide range of complex systems, from ecological collapse to grand mal seizures in the human brain to volcanic eruptions to financial market crashes. The math is well established. The interpretation, when applied to specific real-world systems, is a separate question, and that is where the controversy comes in. The Ditlevsons took the cold blob region's annual mean sea surface temperature record from 1870 to 2020, applied early warning signal analysis to it, and found that both autocorrelation and variance had been growing, statistically, significantly, in a manner consistent with critical slowing down. Their interpretation was that the AMOC, as expressed in the cold blob proxy, is approaching a tipping point. They then fitted a stochastic model to the trend, projected it forward, and computed the time at which the system would, in the model's framing, lose stability and transition to the alternative state. The central estimate was 2057. The 95% confidence interval ran from 2025 to 2095, 2057. That is roughly 30 years from now. Many people watching this video will still be alive in 2057. Many of you will be middle-aged, some of you will be retired, some of you will be raising children who are not yet born. And in the central estimate of a peer-reviewed Nature Communications paper, that is the year when the Atlantic conveyor belt enters a state of full collapse. Now, I want to be very, very honest with you about what this paper does and does not say, because the controversy around it has been substantial, and your skepticism muscle should be active here. The Ditlevsons did not predict that the AMOC will collapse in 2057. What they did was produce a single statistical estimate with substantial uncertainty, based on one specific methodology applied to one specific proxy of AMOC strength. The paper has been criticised on several technical grounds. The cold blob temperature record they used, while long, is not a clean direct measurement of AMOC strength. It is a fingerprint that depends on multiple atmospheric and oceanic factors. The early warning signal mathematics, while well validated in some systems, has been challenged when applied to climate time series of this length, where the noise level is high and the underlying signal is buried in decades of confounding variability. And the assumption that the past trend in early warning signals can be linearly extrapolated forward to estimate a tipping year requires a level of confidence in the model that some oceanographers, including some of the lead AMOC scientists at the National Oceanography Centre, and at NOAA have publicly questioned. So the paper is not the final word. It is one piece of evidence in a larger picture, but it is also not nothing. Because here is the thing. Even if you discount the central 2057 estimate, even if you say the methodology is too aggressive, even if you push the central year back to 2070 or 2080 or 2090, the simple fact that a peer-reviewed analysis in a top-tier journal can produce a 95% confidence interval whose lower bound is 2025 and whose central estimate sits within the lifetimes of most people watching this video is, by itself, a kind of breaking news. Climate scientists have for 30 years treated AMOC collapse as a low probability outcome to be considered for the 22nd or 23rd century, if at all. The IPCC-AR6 report published in 2021 classified AMOC collapse as very unlikely before 2100, but explicitly noted low confidence in that assessment due to model limitations. The Ditlevsons didn't manufacture the concern. They quantified, in a single specific number, what a portion of the climate science community had been saying in informal language for years. Stefan Rahmstorff, one of the lead authors on CESA 2018, who has been studying the AMOC for 35 years, has stated publicly that he believes there is a greater than 50% chance of an AMOC shutdown in the middle of this century. He has described a potential collapse as one of the most dramatic climate changes in the last 100,000 years. Nicholas Beers in 2021 published an analysis in Nature Climate Change suggesting the AMOC may have already lost stability and be approaching a critical transition. Peter Cox at Exeter, writing in a separate methodology, has argued for the use of emergent constraints on AMOC sensitivity that suggest faster than modelled response to warming. The point is not that one paper said one thing. The point is that a substantial cohort of senior, well-published, well-respected AMOC scientists have, over the last 5 to 7 years, become collectively much more concerned about the timeline than they were a decade earlier. And the Ditlevson 2023 paper, controversial as it is consistent with that broader shift in concern. 2057. Hold that number in your head for the rest of this video. Because everything else we're about to discuss, the historical analogue from the Younger Dryas, the Stommel bistability hysteresis, the Portman 2026 emergent constraint, the consequences for Northern Europe and the United States East Coast and the Sahel, all of it is going to circle back to the same question. Is the central estimate too aggressive? Is 2057 the worst case bound? Or is it actually the right ballpark? And have we been collectively underestimating, in our climate models and our IPCC reports and our policy planning, how fast the engine can actually fail? Because the only way to answer that question, the only way to ground truth a statistical projection about a system you have never directly observed in collapse, is to look at the last time it actually did collapse, to find the historical analogue, to see what the planet looked like on the other side of an AMOC tipping point, and we have an analogue. We have probably the most detailed record of a climate flip in the entire geological history of the planet. It happened 12,900 years ago, it hit Europe like a hammer, and it lasted 1,200 years. Part 7. 12,900 years ago. 12,900 years ago, the planet was slowly waking up from the last ice age. The great continental ice sheets were retreating. North America was in the slow process of being deglaciated. Europe was warming. Sea levels had risen substantially from their last glacial maximum lows. Plants were colonizing land that had been frozen for tens of thousands of years. The first wave of human migration into the Americas was happening or had recently happened. The Northern Hemisphere had been on a roughly 2,000-year warming trajectory, and the climate, as far as the evidence shows, had been steadily approaching modern interglacial conditions. Things were warming up. Things were getting better if you happened to be a hominid trying to survive in Northern Europe, and then, almost overnight in geological terms, the climate slammed back into glacial conditions. The event is called the Younger Dryas. It is named after Dryas octopetala, a small white flower native to cold tundra environments whose pollen suddenly reappeared in European lake sediments at a time when it should have been retreating northward as the climate warmed. The flower, in essence, came back. And not just the flower, the whole tundra biome came back. Cold-adapted vegetation, cold-adapted insects, cold-adapted mammals. Across northern Europe, in a window estimated by ice core chronologies to be as short as 1 to 3 decades, the climate flipped from late glacial recovery back into full glacial conditions. The numbers are staggering, and I want you to actually hear them. The Greenland ice core record shows Northern Hemisphere average temperatures dropping by roughly 10 to 15 degrees Celsius within decades. That is not a typo, and that is not a model output. That is what the actual oxygen isotope record of the GISP2 and NGRIP ice cores says happened. 10 to 15 degrees Celsius of cooling, decadal scale onset, across the entire Northern Hemisphere, maintained for approximately 1200 years. Then, equally abruptly, the climate flipped back, again over decades, and the modern Holocene warm period began. And the modern Holocene warm period is the climate state we have been living in ever since. The one in which agriculture became viable, the one in which cities were built, the one in which civilization, in the conventional sense of the word, exists. The Younger Dryas was not a small thing. It was the climate flipping, twice, within a span of 1400 years, and the leading scientific explanation for both flips, supported by sediment evidence from across the Atlantic and lake records from North America, is that an enormous outburst of glacial meltwater from a body of water called Lake Agassiz drained into the North Atlantic and shut down the AMOC, and then, when the meltwater slowed and salinity recovered, the AMOC restarted. I want to spend a moment on Lake Agassiz because it is one of those geological footnotes that turns out, on closer inspection, to be one of the most consequential bodies of water in human history. Lake Agassiz was a proglacial lake, which means it was a lake of meltwater, dammed up against the southern edge of the retreating Laurentide ice sheet, the great continental glacier that covered most of Canada and the northern United States during the last ice age. As the Laurentide retreated, meltwater pooled in the depression between the ice and the higher terrain to the south. At its peak extent, Lake Agassiz covered roughly 440,000 square kilometres, an area larger than all 5 of the modern Great Lakes combined. It held an enormous volume of cold, fresh, newly melted water, and it was sitting there, dammed, waiting for the right moment to release. The moment came. The exact mechanism is still debated, but the most likely scenario is that the southern edge of the Laurentide retreated past a critical drainage threshold, and Lake Agassiz suddenly catastrophically drained, either through the St. Lawrence River system into the North Atlantic, or through the Mackenzie River system into the Arctic Ocean, which then connected to the North Atlantic. Either route delivered the same payload. A massive freshwater pulse, something on the order of 9,500 cubic kilometres of meltwater, give or take depending on the reconstruction, dumped into the North Atlantic over the course of, at most, a few decades. And that freshwater pulse did exactly what Greenland is currently doing in slow motion. It capped the surface of the North Atlantic with a layer of cold, fresh, low-density water, blocked the formation of North Atlantic deep water, and shut down the AMOC. What happened next is the part that should haunt anyone watching this video. Within decades, the northward heat transport that had been keeping northern Europe warm collapsed, not just slowed, collapsed. Sea ice extended south. The North Atlantic drift dissipated. Air temperatures over Europe plummeted. The Sahara, which had been moister during the late glacial period, dried out. The African and South Asian monsoons weakened or shifted south. Tropical rainfall belts, including the ones that fed the headwaters of the Nile, reorganised. And once the AMOC had shut down, the climate stabilised in a new cold regime and stayed there. For 1,200 years. 1,200 years. To put that in human terms, 1,200 years is the entire span from the founding of Rome to the fall of the Western Roman Empire. 1,200 years is longer than the time from the Battle of Hastings to today. 1,200 years is longer than any continuous human empire in recorded history. That is how long the Younger Dryas cold period lasted. 1,200 years of glacial conditions, 1,200 years of frozen Europe, 1,200 years of dried Sahara, 1,200 years of weakened monsoons, 1,200 years of a climate state utterly unlike the one humans built civilization in. And then, abruptly it ended. The AMOC restarted, the climate flipped back, and the Holocene, the warm interval we live in, began. The Younger Dryas is not the only example of an AMOC shutdown in the paleoclimate record. It is just the most recent and most detailed. Going further back, ice core records from Greenland show a sequence of similar events called Heinrich events, named after the German marine geologist Hartmut Heinrich, who first identified them in abyssal Atlantic sediment cores. Heinrich events are episodes where massive armadas of icebergs drained off the Laurentide ice sheet into the North Atlantic, dumping freshwater and sediment-laden ice into the same patch of ocean where the AMOC sinks. There were 6 major Heinrich events during the last glacial period, designated H6 through H1 in chronological order. Each one corresponded to an abrupt climate transition, with abrupt cooling in the northern hemisphere and disrupted tropical rainfall patterns. Layered on top of the Heinrich events were the Dansgaard-Oeschger oscillations, a series of approximately 25 rapid climate transitions during the last 100,000 years, each characterized by abrupt warming over decades, followed by gradual cooling over centuries to millennia, then a sudden return to cold conditions. The Greenland ice cores show these oscillations beautifully, with temperature swings of 5 to 15 degrees Celsius happening over windows as short as a single decade. The exact mechanism of Dansgaard-Oeschger events is still debated, but the consensus view involves perturbations to the AMOC, with each oscillation representing a switch between AMOC modes. The bottom line of the paleoclimate record is uncomfortable. The AMOC is not a smoothly varying, gradually responsive system. It is a system with multiple stable states, and during the last 100,000 years, it has flipped between those states roughly 20 times. Each flip produced a northern hemisphere temperature change of 5 to 15 degrees Celsius over a window as short as 1 to 3 decades, and the planet stayed in the new state, in some cases, for over 1,000 years. If that is the historical baseline behaviour of the system, and we are currently doing to that system, the thing the paleoclimate record shows can flip it, namely dumping freshwater into the North Atlantic at an accelerating rate, then the question of whether a similar flip can happen in the modern climate is not a hypothetical. It is a matter of how close we are to the threshold. The Younger Dryas analogue in particular is uncomfortable for a specific reason. The freshwater pulse from Lake Agassiz was approximately 9,500 cubic kilometres, delivered over a few decades. The cumulative freshwater delivery to the North Atlantic from Greenland ice sheet melt since 2002 has been about 5,300 gigatons, which is roughly 5,300 cubic kilometres. We are, at current rates, about 20 years from delivering a Lake Agassiz equivalent of fresh water into the same body of water that received Lake Agassiz, except this time we are delivering it slowly and continuously rather than in a single burst. Whether that distinction matters, whether a slow continuous pulse can have the same effect as a sudden burst, is one of the central scientific debates in this field. The optimistic view is that the slow delivery allows the ocean to mix and equilibrate, so the sinking is suppressed but not catastrophically so. The pessimistic view is that the cumulative effect is what matters, and that the slow delivery is just delaying the same kind of nonlinear collapse the system underwent during the Younger Dryas. We do not know which view is right. The next several decades of observational data, of tide gauges, of mooring measurements, of sediment cores still being analysed will tell us. The Younger Dryas is the historical analogue. It is the worst case. It is what an AMOC collapse looks like, etched into ice cores and lake mud and sediment, with the kind of detail that leaves no ambiguity about what the climate did, and it sits there in the geological record like a dark mirror, reflecting back at us a future that is not theoretical, a future that is documented, a future that, if the freshwater pulse from a single melting ice sheet was enough to trigger it once, the freshwater pulse from a different melting ice sheet might be enough to trigger again. So if the system can flip, and the paleoclimate proves it can, the only remaining question is what determines the threshold. What is the magic number of freshwater delivery, of overturning suppression, of cold blob spread, that pushes the system from a recoverable slowdown to an irreversible shutdown? And to understand that, you have to understand a piece of mathematics laid down in 1961 by an MIT oceanographer named Henry Stommel in a paper that, for over 30 years, sat largely ignored, and now, suddenly, is the foundational text for the entire AMOC tipping point conversation. Part 8, Stommel's Bistability and the Door That Locks Behind You. Henry Stommel was an American oceanographer who, in 1961, published a short, conceptually elegant paper in the journal Tellus titled Thermohaline Convection with two stable regimes of flow. The paper described what is now called the Stommel two-box model. It was a simple thought experiment. Two ocean basins connected by a shallow channel, one basin in the tropics, one in the poles. Surface heat exchange and surface freshwater exchange tend to push the temperatures and salinities of the two basins toward equilibrium. Meanwhile, water can flow between the basins through the channel, driven by density differences. Stommel solved the equations for the equilibrium states of this system, and he found something peculiar. For a wide range of forcing conditions, the system has two stable solutions. One in which the polar basin's water is denser and sinks, driving a strong overturning flow that carries warm water poleward. And one in which the polar basin's water is fresher and lighter, doesn't sink, and the overturning collapses to a weak or reversed flow. In Stommel's model, the system is base-stable, like a light switch with two settings, up or down, strong overturning or weak overturning, and the transition between the two states is not gradual, it is abrupt. Cross the threshold, and the system switches modes. The paper sat for 30 years before its full implications were appreciated. But by the 1990s, with the Younger Dryas and the Heinrich events being characterized in detail, the climate science community recognized that Stommel's B stability was not just a mathematical curiosity. It was the underlying mechanism of every abrupt climate transition in the paleoclimate record. The reason the AMOC flips, when it flips, is that the underlying density structure of the North Atlantic supports two stable regimes, and crossing a freshwater forcing threshold can flip the system from one to the other. There is one more feature of the Stommel model that has to be on the table for this conversation, and it is the most uncomfortable one. The two stable states are not symmetric in their relationship to the freshwater forcing. To switch from strong overturning to weak overturning, you have to push the freshwater forcing past a high threshold. But to switch back from weak to strong, you cannot just bring the freshwater forcing back to where it was. You have to bring it down to a much lower level. This is called hysteresis. The system has memory. The path back is not the path in, and the implication for our current situation is profound. If the AMOC flips into a weak state, simply stopping the Greenland melt is not sufficient to flip it back. You would have to actively reverse the freshwater forcing, to cool the North Atlantic, to refreeze a substantial volume of ice, to overcome the system's preference for the new state. And that, on policy timescales, may not be possible. The door, when it closes, locks behind you. The Lenton et al. 2008 paper in the Proceedings of the National Academy of Sciences identified the AMOC as a tipping element specifically because of this hysteresis behaviour. The tipping element framework distinguishes between climate features that respond smoothly and reversibly to forcing and those that exhibit threshold behaviour with multiple stable states. The AMOC was placed in the highest priority category, alongside the Greenland ice sheet, the West Antarctic ice sheet, the Amazon rainforest dieback, and a handful of other systems. Each of these elements has the property that, once you cross the threshold, you cannot easily go back. The forcing required to push them across is much smaller than the forcing required to pull them back. Whether the real-world AMOC is actually as boostable as Stommel's idealized model is debated. Some recent CMIP6 simulations, the climate models used to inform the IPCC reports, suggest that under realistic forcing scenarios, the AMOC weakens monotonically rather than collapsing abruptly. Others, including the early warning signal analyses we just discussed, argue that the precursors of bistable behaviour are visible in the observational record. The disagreement is the cutting edge of AMOC research, and it is unlikely to be resolved anytime soon. But the precautionary principle, the idea that when the cost of being wrong is large, you act to avoid the wrong, is starting to dominate the policy conversation. If even a moderate probability of Stommel-style B stability is on the table, and the cost of crossing that threshold is 1,200 years of glacial conditions over northern Europe, the calculus is no longer about scientific certainty. It is about decision-making under uncertainty in a system whose downside scenarios are almost unimaginable. So let's bring the science back to the leading edge of where it stands today. Because in 2026, just months ago, a paper landed in Science Advances that changed the way the climate models themselves are being interpreted. And what that paper says, if it holds up, is that the standard CMIP6 projections, the very models that inform every IPCC report and every government adaptation plan, may be systematically wrong about how fast the AMOC actually responds to warming. Part 9, Portman 20. 26 and the models that underestimate. Christine Portman and her colleagues published a paper in Science Advances earlier this year titled, in essence, an emergent constraint on AMOC sensitivity to anthropogenic forcing. To explain what an emergent constraint actually is and why the Portman result is significant, I need to spend a moment on how climate modelling works in practice, because once you understand the structure of the problem, the result becomes much clearer. Modern climate models, the ones used in the IPCC reports, are called General Circulation Models, or GCMs. They simulate the Earth's atmosphere, ocean, sea ice, land surface, and biogeochemistry on a three-dimensional grid covering the entire planet, with grid spacings ranging from a few tens of kilometres to about 100 kilometres depending on the model. The models solve the equations of fluid motion, radiative transfer, thermodynamics, and a long list of other processes, and they propagate the system forward in time-on-time steps as short as a few minutes for the atmosphere and a few hours for the ocean. They are extraordinary engineering achievements, but they are not exact. Many physical processes in the climate system happen on scales much smaller than the model grid and have to be parameterized, which is to say, approximated by simplified equations whose parameters are tuned to match observations. Cloud formation, turbulent mixing in the ocean, sea ice ridging, convection. Each of these processes has tunable parameters, and different climate models make different choices. The result is that the world's climate models, the roughly 30 or 40 of them that participate in the Coupled Model Intercomparison Project, or CMIP, do not all agree. They produce a range of projections for any given forcing scenario. The range, the multi-model spread, is the source of much of the uncertainty in IPCC projections. For some quantities, like global mean surface temperature, the models agree pretty closely. For other quantities, like the strength of the AMOC, the models disagree substantially. Across the CMIP6 ensemble, projected AMOC weakening by 2100 ranges from roughly 20% to roughly 40% under standard mid-range emission scenarios. That is a factor of 2 spread, which translates to enormous differences in projected impacts on Northern European climate, sea level rise, and tropical rainfall. So the question is, can you do better? Can you use observational data somehow to constrain which of the climate models is most likely to be right? That is what an emergent constraint does. The idea is to find a present-day, observable quantity that is correlated across the model ensemble with the future projected response. If you can find such a relationship, you can use the observations of the present-day quantity to narrow down the range of plausible future projections. The technique was pioneered by Peter Cox at Exeter and has been applied to a wide range of climate variables, from cloud feedback to Arctic sea ice extent. What Portman and her team did was apply this technique to the AEMOC. They identified a relationship across the CMIP6 ensemble between the present-day pattern of Atlantic sea surface temperatures and the model's projected AMOC weakening over the 21st century. Specifically, models that produced a stronger present-day cold blob, with anomalously cool sea surface temperatures south of Greenland and anomalously warm temperatures along the Gulf Stream, also produced a larger AMOC weakening by 2100. The correlation across the ensemble was strong enough to support an emergent constraint. Then they brought in the observations, the actual observed sea surface temperature pattern in the modern North Atlantic, and they used the observed pattern to narrow down which of the CMIP6 models in the range from 20 to 40% projected AMOC weakening are most consistent with reality. The answer was uncomfortable. The observationally constrained projection was not in the middle of the CMIP6 range, it was substantially toward the high end. The Portman result implies that if the observed sea surface temperature pattern is taken seriously as a constraint, the AMOC will weaken by approximately 50% by 2100, with a confidence range of 42 to 58%. That is, on average, 50% stronger than the central CMIP6 projection, and it sits above the upper end of most individual model results. The implication is that the standard climate models, the very models that have been used to produce every IPCC AR6 projection, every government climate adaptation plan, every regional impact assessment for Northern Europe, the US East Coast, the Sahel and South Asia, are systematically underestimating how fast the AMOC is responding to warming, not by a little, by roughly a factor of 1.5 to 2. And if the AMOC sensitivity is being underestimated, every downstream impact projection that depends on AMOC behaviour is also being underestimated. I want to be careful here. The Portman paper is one paper. It uses one specific methodology applied to one specific observed pattern. Emergent constraints are a powerful technique, but they are not bulletproof, and the climate modelling community is still digesting the result. The honest interpretation is that Portman 2026 is the leading edge of a methodology that suggests the central scientific expectation for AMOC weakening is more aggressive than the IPCC AR6 baseline, and that the models the IPCC relies on are likely undersensitive to freshwater forcing on the North Atlantic. The full implications, whether other emergent constraints corroborate the result, whether the next generation CMIP7 models will incorporate the lesson, is still being worked out in the literature, but the direction of the correction is clear, and the direction is not toward a slower, more gradual AMOC response. It is toward a faster, more aggressive one. The Ditlevson central estimate of 2057 for full collapse, viewed in light of Portman 2026, becomes less of an outlier and more of a plausible mid-range scenario. The Caesar 2018-1600-year low becomes less of a slowly developing trend and more of a system already well into the instability regime. The cold blob becomes less of a passive fingerprint and more of an active warning. Every piece of the puzzle, when you stack the pieces in the order they were published, points in the same direction. The AMOC is weaker than the model said. It is responding faster than the model said. It is approaching, possibly already approaching, the regime where Stommel-style bastability becomes a real-world risk. And the consequences of that, region by region, sector by sector, are going to be profound. So let's actually walk through what a 50% slowdown looks like in practice. Because it is not abstract. It is not far off. It is not science fiction. It is, in the central scientific expectation for the year 2100, a redrawing of the climate map of the entire Atlantic basin. Part 10. What a 50% slowdown actually looks like. Let me walk you through a thought experiment. The year is 2100. The AMOC has weakened by 50%, in line with the Portman emergent constraint. Greenhouse gas emissions have followed something like a middle-of-the-road trajectory. The rest of the planet has continued warming on average, in line with global mean surface temperature projections. The question is, what does the world actually look like? In northwestern Europe, the picture is strange. Most of the rest of the planet is warmer than today. The tropics are hotter, sometimes dangerously so. The Mediterranean is drier. Southern Europe is hotter. But in northwestern Europe, the United Kingdom, Ireland, Norway, the Netherlands, Denmark, Germany, the warming has not happened the way it has elsewhere. Winter temperatures in particular are not warmer than today. They might be the same. They might, in some scenarios, be slightly cooler. The reason is that the AMOC has weakened enough to substantially reduce the northward heat transport that has historically kept those countries warmer than their latitude would suggest. The cold blob has expanded, storm tracks have shifted, jet stream behaviour has become more variable, with more frequent meridional excursions that bring Arctic air south over Europe. The result is that, against a backdrop of global warming, northwestern Europe is experiencing what some climatologists have called regional cooling. Not dramatic cooling, not younger Dryas cooling, but a 1 to 3 degrees Celsius offset against the global mean, which, given that the rest of the world is warming by 2 to 3 degrees, leaves northwestern Europe roughly where it was in 2025. Roughly. With caveats, because the variability has increased. Cold winters, like the brutal 2017 to 2018 winter, become more common. Persistently cool, grey, wet summers, like the early 2020s pattern in the British Isles, become more common. Crop yields begin to fluctuate in ways European agriculture is not adapted to. Heating fuel demand stays high, even as the rest of Europe transitions to cooling-dominated energy systems. Coastal storms become more energetic, because the increased temperature contrast between the cold subpolar Atlantic and the warming tropics drives stronger atmospheric pressure gradients, which means more intense extratropical cyclones tracking across Western Europe. In the United States, the story is different. Sea level rise along the East Coast accelerates beyond what it has already been doing. We talked earlier about how cities from New York to Miami are already seeing sea level rise at 3 to 4 times the global mean rate. With a 50% AMOC slowdown by 2100, that anomalous regional rate continues, and the cumulative offset above global mean reaches an additional 10 to 30 centimetres by the end of the century in some projections. that 10 to 30 centimetres is on top of global mean sea level rise of roughly half a metre to a metre, depending on emissions trajectory and ice sheet behaviour. Combine the global rise with the AMO sea-driven regional offset, and you are looking at an east coast that has experienced effective sea level rise on the order of 1 to 1.5 metres by 2100, in cities including Boston, New York, Norfolk, Charleston, Savannah, Jacksonville and Miami. The implications for coastal flooding, saltwater intrusion into aquifers, infrastructure resilience, real estate markets and insurance pricing are not abstract. They are operational. Cities are already redrawing flood maps and planning seawall projects. The acceleration of regional sea level rise driven by AMO sea weakening turns a manageable adaptation challenge into a much harder one on a much shorter timeline. In the tropics, the consequences are perhaps the most far-reaching and the least discussed in mainstream Western coverage. The AMO sea carries an enormous amount of heat across the equator from south to north. When the AMO sea weakens, that cross-equatorial heat transport weakens, and the Atlantic intertropical convergence zone, the band of equatorial rain that determines whether the African Sahel and the South Asian monsoon get adequate rainfall shifts. Specifically, it shifts southward, away from its historical position. The Sahel, the semi-arid belt of Africa stretching from Senegal in the west to Sudan in the east, depends entirely on the location of the ITCZ for its monsoon rainfall. A southward shift of the ITCZ by even a few hundred kilometres can be catastrophic for Sahelian agriculture. We have a historical analogue for this, ironically, in the Younger Dryas, when the ITCZ shift produced widespread drying across the Sahel, and in the more recent African drought of the 1960s through 1980s, when natural decadal variability in Atlantic sea surface temperatures produced a sustained southward ITCZ shift and triggered famine across the region. A 50% AMOC weakening in essentially every climate model that has been used to study it produces an ITCZ shift comparable to or larger than the natural variability events of the late 20th century. The implications for the roughly 400 million people who live in the Sahel, and for the broader food security of West Africa, North Africa, and parts of southern Europe that depend on Sahelian agricultural exports, and that would be destination markets for climate-driven migration, are difficult to overstate. The South Asian monsoon, which feeds roughly 2 billion people across India, Pakistan, Bangladesh and Southeast Asia, is also linked to North Atlantic sea surface temperature patterns through atmospheric teleconnections, although the connection is more diffuse. A MOC weakening tends to reduce monsoon intensity in some regions, while shifting timing in others. The net effect on agricultural productivity in South Asia is hard to quantify, but the consensus direction is negative. In the global ocean, the consequences extend beyond regional climate impacts. North Atlantic fisheries, which depend on the productivity driven by upwelling and frontal zones associated with the AMOC, experience further range shifts and population collapses. Cod stocks, which have already collapsed and barely recovered in places like the Grand Banks, face additional stresses as warmer southern fish species move northward and cooler adapted species lose habitat. Atlantic salmon runs are disrupted. The bottom-up reorganisation of marine food webs in the North Atlantic already underway accelerates. In the Amazon, the shifted ITCZ'd and altered tropical precipitation patterns push the rainforest dieback risk into faster trajectories. The Amazon, like the AMOC, is a tipping element in its own right. The two are coupled in the sense that AMOC weakening affects tropical Atlantic SSTs, which affect Amazon precipitation, which affects the rainforest's ability to maintain itself against deforestation pressure. A weakened AMOC compounds the existing pressure on the Amazon and increases the probability that it crosses its own tipping point sometime this century. In the Antarctic, the picture is genuinely strange. There is some evidence from climate models that AMOC weakening, by reducing northward heat transport, leaves more heat in the Southern Ocean, which can accelerate Antarctic ice shelf melting and West Antarctic ice sheet instability. So the AMOC weakening that began with Greenland melting could, in turn, accelerate Antarctic melting, which would feed back into global sea level rise and further alter ocean circulation. The system is coupled. The dominoes tip into each other. The honest summary of a 50% AMOC slowdown by 2100 is that it produces a fundamentally redrawn climate map of the Atlantic basin. Not a Younger Dryas style flip into glacial conditions. Not a Hollywood movie where Manhattan freezes overnight. Something more diffuse, but in some ways more pervasive. A slow, persistent reorganization of where rain falls, where storms track, where coastal flooding happens, where agricultural belts can sustain themselves. A reorganization that the existing infrastructure of the Atlantic Basin, its cities, its farms, its fisheries, its insurance markets, was not designed to accommodate. And that is the central scientific expectation. Not the worst case, the middle case. The thing the leading edge of climate science currently expects to happen, on a timeline that includes the lifetimes of most people watching this video. If that is the central case, then the worst case, the full Stommel-style collapse with younger Dryas analog consequences, is the tail risk. And the question of how seriously to take that tail risk, and how much of it has been deliberately hidden from public discussion, is where the conspiracy and counter-narrative theories come in. Some of those theories are unhinged. Some of them surprisingly point at real gaps in the public conversation, so let's go through them. Part 11. Conspiracy, Cover-Up, and the Honest Version. Whenever a story like this enters the public conversation, a story about a tipping point in an enormous natural system, with potentially catastrophic consequences, with a timeline that may sit inside the next several decades, the conspiracy theories come for it. That is just what happens with high-stakes science in the modern information environment. So I want to walk through the most common AMOC conspiracy framings, Steelman each one, and then tell you what I actually think the science says. Because some of these are easier to dismiss than others. The first claim is that the AMOC weakening is being deliberately suppressed by governments and mainstream media to protect fossil fuel interests. The Steelman version notes the gap between scientific findings and policy response, which is real. The IPCC says the AMOC is a tipping element. Governments continue to expand fossil fuel infrastructure. There is, on the surface, a contradiction. The rebuttal, though, is structural. AMOC research is being published openly in the highest impact peer-reviewed journals on the planet: Nature, Science, Nature Climate Change, Nature Geoscience, Science Advances. It has been covered by every major international news outlet from the BBC to the Washington Post. The IPCC AR6 explicitly identifies the AMOC as a tipping element. There is no observable suppression. The gap between scientific consensus and policy action is real, but it is a political and economic problem, not a censorship problem. The science is in the open. The question is whether anyone in power is acting on it. The second claim is that geoengineering, weather modification, HAARP, cloud seeding, stratospheric aerosol injection is causing the AMOC weakening. The Steelman version invokes the same general framework as other weather modification conspiracy theories. The rebuttal is the energy budget argument that comes up over and over in conversations like this one. The freshwater flux from Greenland ice sheet melt, 270 gigatons per year, represents an energy injection into the North Atlantic on the order of 10 to the 21st to 10 to the 22nd joules per year, just in the latent heat of the ice that has melted. The cumulative energy output of all proposed and operational geoengineering interventions worldwide is, at most, 10 to the 15th to 10 to the 17th joules per year. The geoengineering signal is 6 to 7 orders of magnitude too small to be a plausible driver of AMOC weakening. Even if every cloud seeding program on Earth were maximally effective, even if HAARP were doing things HAARP is not actually doing, the energy budget does not work. The Greenland melt rate by itself fully accounts for the observed forcing on the North Atlantic. There is no need to invoke any other cause, and nothing in the geoengineering literature supports the magnitude required. The third claim is that the AMOC will collapse imminently, within the next 5 to 10 years, and authorities are hiding this to prevent panic. The Steelman version cites the 2025 lower bound from the Ditlevson confidence interval. The rebuttal is twofold. First, the 2025 lower bound represents the bottom of a 95% confidence interval for a single statistical analysis whose methodology has been questioned by parts of the oceanographic community. The central estimate is 2057, not 2025. Second, AMOC monitoring, rapid, OSNAP, the satellite altimetry network, would show pronounced acceleration of weakening if the system were actually on a year to 5-year collapse trajectory. The current observational record shows continued weakening at trend rates, not the kind of non-linear acceleration that would precede an imminent collapse. The honest scientific position is that imminent collapse is possible, but not the central estimate, and that observational systems would detect it before it happened. Worth watching closely. Not worth panicking over. The fourth claim is that the AMOC weakening is part of a natural cycle, the Atlantic multi-decadal oscillation or solar cycle effects or similar, and is not driven by anthropogenic warming. The Stillman version observes that the Atlantic multi-decadal oscillation does produce decadal to multi-decadal variability in North Atlantic sea surface temperatures, and that the post-2004 rapid record alone is too short to fully separate trend from variability. The rebuttal is paleoclimate-based. Thornalley, 2018 sediment cores show that the post-1850 AMOC weakening is unprecedented in the 1600-year record, far exceeding any prior natural variability cycle visible in the proxy data. Caesar 2018 explicitly addresses the AMO versus anthropogenic question and shows that the spatial pattern of the cold blob is inconsistent with a natural AMO signature and consistent with the predicted anthropogenic forcing fingerprint. The natural cycle hypothesis cannot explain the magnitude of the observed weakening. Internal variability is real, it produces noise, it does not produce a 1600-year low. The fifth claim is the inverse of the others. The AMOC is fine. Climate scientists are exaggerating the risk for funding and policy reasons. The Steelman version observes that the AMOC research community has, in the past, occasionally produced findings that turned out to be premature. The early 2000s AMOC shutting down headlines based on the Bryden et al. 2005 Nature paper, which were later substantially revised when longer time series became available. The rebuttal is that the 2005 Bryden result was a single snapshot measurement that was indeed revised when continuous monitoring, rapid beginning 2004, provided longer time series, but the longer time series did not eliminate the weakening trend. It confirmed it at a slower rate. Subsequent paleoclimate, fingerprint, and observational constraint analyses have all converged on the same direction of change. The current scientific consensus is the result of multiple independent lines of evidence, not single-paper sensationalism. The exaggeration narrative does not survive contact with the evidence stack we have walked through in this video. The honest version of all of this, the version I actually believe based on reading the literature and tracking the field, is that the AMOC story is not a conspiracy. It is not a cover-up, it is not exaggerated, it is also not imminent in the catastrophic sense. It is a slow-motion crisis, well documented in the open scientific literature, whose timeline is genuinely uncertain, but whose central case implications are large enough to warrant the kind of emergency-scale mitigation response that the world has, so far, not produced. The frustration that drives the conspiracy theories is not entirely misplaced. The gap between what the science says and what governments are doing is genuinely large. The conspiracy theories just point at the wrong cause. The cause is not censorship. The cause is policy inertia in the face of a problem that is well understood. And that brings us to the last and most important question of this video, the one all the others have been pointing at the entire time. Is the AMOC right now in the process of crossing the threshold from which it cannot recover? Are we, in real time, on the planet we live on, watching a tipping element tip? Part 12. Are we flipping it now? Let me bring this all the way home. The question that every line of evidence we have walked through is pointing at. The question that the Caesar fingerprint, the Thornalley sediment cores, the rapid array, the Greenland gravimetry, the Stommelby stability, the Younger Dryas analog, the Ditlevson early warning signals, and the Portman emergent constraint are all collectively trying to answer, is the same question. Are we flipping it now? Have we already pushed the AMOC past the threshold from which it cannot recover? Are the next several decades of monitoring data going to show the slow weakening of the past few decades transitioning into a non-linear runaway collapse? The honest answer, and I'm going to be very precise here because I do not want to mislead you, is that we do not know. Not because the science is bad, not because the data is hidden, not because there is some grand uncertainty that will never be resolved. We do not know because the system is large, slow, and enormously complex, and the difference between approaching a tipping point and crossing it is, on the timescale we observe, almost indistinguishable from continued slow weakening. The signals that would tell us the threshold has been crossed are signals that, once visible, indicate the transition is already underway and largely unstoppable. That is the cruel feature of tipping elements. They do not announce themselves. They do not put up a warning sign. The moment the system has visibly tipped is the moment intervention becomes nearly impossible. The window of agency, the period during which mitigation can still prevent the tipping, is the period during which the threshold has not yet been observably crossed. By the time you can see it clearly, you have already lost it. So you have to act on probability. You have to act on partial evidence. You have to act on the converging signal of multiple independent lines of evidence, even though no single line of evidence is, by itself, conclusive. The paleoclimate record says the system can flip. The fingerprint says the system is currently in its weakest state in 1600 years. The direct mooring measurements say the system has weakened by 15% over the satellite era. The early warning signals say the system is exhibiting statistical precursors to a tipping point. The emergent constraint says the climate models have been underestimating sensitivity. The Greenland melt rate says the freshwater forcing that drives the weakening is accelerating. None of these in isolation is proof. All of them together is a chorus. Stefan Rahmstorff, who's been studying this system for 35 years, says greater than 50% probability of shutdown by the middle of this century. Nicholas Boers says early warning signals are already visible in salinity data. The Ditlevsens say the central estimate for full collapse is 2057. The IPCC AR6 says collapse is very unlikely before 2100, but with low confidence in that assessment. Christine Portman says CMIP6 is underestimating sensitivity by a factor of 1.5 to 2. The chorus is not unanimous. There is healthy scientific disagreement about timing, about magnitude, about whether bistability is the right framework. But the disagreement is about the details. The direction is settled. I want to tell you what I think, with the caveat that I am a science explainer and not a research scientist, but I have read the literature carefully, I have followed the debate for years, and I think you deserve a clear opinion rather than another carefully hedged summary. I think the AMOC is in trouble. I think the trouble is more serious than the IPCC AR6 baseline projects. I think the Portman correction to CMIP6 sensitivity is broadly correct. I think a 50% weakening by 2100 is the central case, not the worst case, and I think the regional impacts of that weakening on Northern Europe, the US East Coast and the Sahel are going to be substantially worse than current adaptation planning assumes. I think the probability of full collapse this century is genuinely uncertain, somewhere between 5 and 30% depending on emissions trajectory and unknowable physical thresholds, and I think that probability is large enough given the magnitude of the consequences to warrant emergency scale mitigation effort. I think the Ditlevsen 2057 central estimate is too aggressive in its specific year and too narrow in its confidence interval, but its broader message that the collapse window may sit inside this century rather than the next is consistent with the rest of the converging evidence. I think the next 10 to 20 years are going to be decisive. If the AMOC weakening continues at trend rates, the central case scenarios stay in play and we have time to respond. If the weakening accelerates, the collapse window shortens dramatically. If new monitoring, the OSNAP array, the Abyssal Argo network, the next generation of satellite altimetry detects non-linear behavior in the subpolar gyre, the conversation will shift. If sea level rise on the US East Coast keeps accelerating in the next decade, that is the AMOC fingerprint compounding. If Greenland melt rates keep climbing, that is the freshwater forcing compounding. If the cold blob deepens or expands, that is the surface fingerprint compounding. Each of those signals is a piece of the answer to the question, are we flipping it now? The Younger Dryas proves it can flip. The paleoclimate record proves it has flipped many times before. The current evidence stack proves it is currently in its weakest state in 1600 years. The mathematics proves there are stable states the system can transition to, and transitions can be abrupt. The Greenland ice sheet is bleeding into the very patch of ocean that has tipped before. The cold blob, the warmer Gulf Stream, the East Coast sea level, the Sahel rainfall, all of the fingerprints are visible. They are visible right now, on the planet you are sitting on, in the climate you are living in. Whether the threshold is crossed in 2057 or 2070 or 2085 or 2120 does not, I think, change the moral calculus very much. Each of those years sits inside the lifetime of someone alive today. Each of them represents a future that is closer than the conventional climate conversation has acknowledged. Each of them carries consequences, regional and global, that the existing infrastructure of human civilization is not prepared for. The honest precautionary position is that even a low probability of an AMOC collapse this century is too costly to ignore. The cost of being wrong about an AMOC tipping point is comparable in regional climate impact to the consequences of a moderate nuclear war or a major asteroid impact. We do not run our societies, our militaries, or our financial systems on the assumption that low probability, high consequence events are not worth preparing for. And yet somehow, when the threat comes from inside the climate system, from a process that is invisible, gradual, and named with an acronym most people have never heard, we treat it as background noise. It is not background noise. It is the largest moving heat machine on the planet slowing down on a trajectory that has the leading edge of climate science genuinely worried on a timescale that includes everyone watching this video. And the only honest answer to the question, are we flipping it now, is that we cannot say with certainty, but the converging evidence makes it impossible to rule out. We are inside the period of agency. We are in the window where the threshold has not yet been observably crossed. We are looking at fingerprints, not corpses. The question is whether we choose to act on the fingerprints before we have to act on the corpse. The Atlantic conveyor belt has been running for the entire span of human civilization. It has built every empire on the Atlantic basin. It has fed every harvest in Northern Europe. It has stabilized the climate that allowed the rise of cities, the rise of literacy, the rise of agriculture, the rise of everything we recognize as modern human existence. It has been so reliable, so quiet, so unspoken in the background of our world that for thousands of years no one even knew it was there. We know it is there now. We know it is slowing. We know that 12,900 years ago, when it slowed before, it did not slow gracefully. It snapped, and the climate stayed snapped for over 1,000 years. Whether that happens again is, in some real sense, no longer a question of physics. The physics is doing what the physics is going to do. Greenland is going to keep melting at whatever rate the global temperature drives. The North Atlantic is going to keep freshening at whatever rate the freshwater pulse delivers. The conveyor belt is going to keep slowing at whatever rate the freshwater forcing dictates. The remaining variables, the only variables that humans get any say in at this point, are how much carbon dioxide we keep adding to the atmosphere, how fast we slow Greenland's melt by slowing the warming, and how quickly we build the monitoring systems that will tell us, in real time, if the threshold is being crossed. The Atlantic Ocean has been writing us a letter for the last 50 years. It has been writing it in cold blob anomalies. It has been writing it in sediment grain sizes. It has been writing it in tide gauge records along the east coast. It has been writing it in foraminifera fossils in the Labrador Sea. It has been writing it in the speed of the Gulf Stream, in the thickness of Greenland's ice, in the salinity of the subpolar gyre, in the pixel-by-pixel temperature record of every weather satellite that has flown. The letter says, the engine is failing. The letter says, I have failed before, and the consequences were severe. The letter says, you are still inside the window where you can choose. The letter says, I will not write this letter forever. The letter says, look up. 12,900 years ago, this exact ocean in this exact place snapped from one stable state into another. A continent that had been warming for 2,000 years froze in less than 3 decades. The cold lasted 1,200 years. We're doing to the same ocean, in the same place, the same thing we know will trigger the same response. The question is not whether the climate system can flip. The question is whether we are flipping it now. And the answer, the only honest answer, is that we are watching it weaken in real time on every instrument we have, and the period during which we get to find out the answer is also the period during which we still have agency over what the answer turns out to be. I want to leave you with one last piece of perspective, because I think it is important to sit with the scale of what we are actually talking about. Henry Stommel, the oceanographer who first wrote down the bistability mathematics in 1961, was working with pencil and paper and a slide rule. He had no satellite data, he had no grace gravimetry, he had no rapid array, he had no sediment cores at the resolution we now have. He had a few decades of hydrographic measurements, the basic equations of fluid dynamics, and an extraordinary intuition about how oceans actually behave. and from that he wrote down a simple two-box model that predicted, on theoretical grounds alone, the existence of a tipping point in the Atlantic conveyor. 6 decades later, satellites we did not have when Stommel was writing have measured the cold blob. Sediment cores we did not have when Stommel was writing have measured the 1600-year low. Mooring arrays we did not have when Stommel was writing have measured the 15% weakening. And every one of those measurements has been consistent with the theoretical framework Stommel laid down with pencil and paper in 1961. That is what scientific consensus actually looks like, when it forms slowly across decades, across multiple independent groups, across multiple independent methodologies, all converging on the same conclusion. It does not look like a press release. It does not look like a single panicked headline. It looks like Henry Stommel in 1961 writing down a piece of mathematics that nobody appreciated for 30 years, and then a generation of oceanographers, working quietly in places like Potsdam and Woods Hole and Southampton and Copenhagen, building, over 6 decades, the empirical foundation that confirmed the theoretical framework was right. The AMOC tipping point story is not a sudden discovery. It is the slow ripening of a 6-decade-old theoretical insight into a fully observed phenomenon, and we are the generation that gets to see the ripening. That is, in some ways, a privilege. The amount of physical understanding of the climate system available to us right now, the amount of monitoring capability, the amount of integrated theory and observation is greater than at any time in human history. We can see things our grandparents could not have imagined seeing. We can measure things our parents would have called science fiction. The cold blob, the gravimetric Greenland melt, the abyssal ocean currents, the early warning signal mathematics, the emergent constraint methodology, all of it is the inheritance of 6 decades of patient, quiet, mostly unnoticed work by tens of thousands of scientists. They have laid this picture down for us, piece by piece, paper by paper, year by year. The question is what we do with it. Look up. Look at the ocean. Look at the cold patch on the satellite map. Look at the tide gauge in your nearest coastal city. Look at the latitude of London. Look at the latitude of Hudson Bay. Look at what stands between the two of them. Look at the meltwater pouring off Greenland in real time, on satellite imagery you can pull up on your phone in about 30 seconds. Look at the ITCZ creeping south. Look at the sediment cores in the Iceland Basin and the Labrador Sea. Look at the chorus of papers in the highest impact journals on Earth, all telling you the same thing in different methodological accents. Look, just look. And then ask yourself, when the engine that has been holding all of this together for the entire span of human civilization quietly switches off, who exactly is going to notice in time to do anything about it? Because the next clue, the next piece of the puzzle, the next fingerprint in this story, may already be on its way. And when it arrives, the only people who will see it coming are the ones who are already looking. The ocean has been writing the letter for 50 years. The question is not whether the letter exists. The question is whether anyone in the rooms where decisions actually get made is reading it. And whether the rest of us, the people watching the satellite maps and the tide gauges and the channels like this one, can collectively make enough noise about what the letter says before the letter stops being a warning and starts being a postcard from the other side of the threshold,